Hello everyone, welcome back. Today we're going to have a look at the grade 12 question paper 1 physical sciences of November 2021. So we're going to have a look at question 8 that will be focusing on electrical circuits. So the statement we are given there is that a battery in the circuit is connected as shown in this diagram, and it has an EMF of 12 volts and an unknown internal resistance. The resistance of the connecting wires, they are saying we must not consider them or they are negligible. And the first question is asking us to please state the reading on the voltmeter 1 and voltmeter 2. All right. So before we dive into that question, I would just like to point out the components that make up this circuit. The first one is a battery and an internal resistance, as they have stated in the question. They are telling us that the EMF of the battery is 12 volts. We also see a resistor. We see an ammeter here. Resistor, and a voltmeter. Here's the first voltmeter. So just to give us a brief introduction to what all these components are doing in here. The first one, the easiest one, is the switch. A switch is either on, so it has this leg here. So we'll have something like this. This is being on and this is being off. As you can see, when it's on, this part of the circuit is connected to this part. When it's off, this part is separated from this part, which means depending on the location of the switch, there won't be current moving forward. So we know that this is the battery. If current is moving here, when it gets here, it will stop. We don't have a path to flow that side. So there's no current flowing into the entire circuit if the switch is here and it's off. The second part is, of course, the battery and then an internal resistance. A battery, as we are most familiar with, ages with time. If you buy a battery or an AA or a AAA battery, or you buy a battery for a torch, let's say it's written 5 volts. The battery is written 5 volts. It looks like that. It has a plus and minus here. As time goes by, this battery will no longer be able to produce that entire 5 volts because it's aging with time. So it's being eaten up by the internal components that make up the battery. So we call those components the internal resistance. As it grows or as time lapses, the voltage that we read across the battery, when there's current moving, it decreases with time because it's being eaten up by the internal resistance. So that's an internal resistance, that's an internal resistor, and that's a battery. The other components, these are resistors. What does a resistor do? As I've shown you here, a resistor drops potential difference, or it eats up voltage. What does that all mean? It means that a resistor resists or opposes or doesn't, or it's a way of limiting the current flow. So if current is flowing in this direction, or let's say this is a river, there's water here, and there's another river with stones. Yeah, let's say both of these rivers are connecting to the major river. If this water sees that, let's say it sees that there are stones here and here, we're just moving swiftly, what the water will tend to do is that most of it will be flowing that side, but because not everything will fit within that small river, So minor water will be going through the river that has, or the path that has stones. What does this mean in internal or in resistors and also electrical circuits? When current is moving, when current is flowing, it will always choose the path of less resistance, or the less rocky path, the path that won't cause damage to current, if we can look at it like that, or the path according to this water that won't inhibit the water from flowing nicely. So when you speak of resistance in an electrical circuit, it is a component that decreases, or rather makes it hard for current to flow. And those are the components. They are important in a circuit to limit voltages at certain points in our electrical circuit. So that's just the introduction to the components that make up this entire circuit. Now we're going to dive into question 8.1.1. Now, the question is asking us what is being read on voltmeter 1. And this is all happening when switch S is open. Remember what I've mentioned, when the switch is at this position, no current is flowing here. When it's lying there or in an on state, then there's current. So they're asking us the voltage when across the battery. So this is the battery. When the switch is open, like I told you, when a battery has current flowing through it, we hope that it gives us the voltage that was stated when we bought it from the shop. But because of the internal resistances, it drops. But do note that in this circuit, we have the battery, we have a resistor, and these are not connected to the circuit. So we know that in order for voltage to drop in a resistor, so voltage across a resistor is equal to current multiplied by the resistance. Now that the switch is open, it means the current is equal to 0 amps. The resistance is equal to that resistance there, which is R. We haven't yet calculated it. So we know that the voltage that is being dropped across this resistor is going to be 0 multiplied by R, which is 0 volts. So we already know we have 0 volts here. Therefore, the battery must read the entire EMF. So the answer to 8.1.1 is that V1 is equal to 12 volts. 8.1.2. is asking us the voltage reading on this voltmeter. Now, like I said, when the switch is open, it means that current might try to be pushed by this this battery, but because of the open circuit nature, there won't be current flowing. So it means that across this entire point, there's no current, 0 amps flowing. So even when it divides here, there's still 0 amps flowing here, 0 amps flowing that side. So now when calculating what is the voltage that is being read across that resistor, you can either just by looking at the circuit, there's no current flowing through there, so there's no voltage being read. But to be quite specific, we should say we have a resistor, 6 ohm, and we have current here, but that current is 0 amps. And using this formula, V across 6 ohms is equal to I times R. What is the resistance? 6. What is the current? 0. So 0 times 6, that's 0 volts. So the voltage that is read across the 6 ohm is 0 volts. Alright, now we're going to move to question number 8.2. Now the switch is closed. Now I'm just going to erase this. Now they are saying we must close the switch. The first question is, let us define what is power. Okay. So, as we all know that, or as we all should know that, energy is defined as the ability to do work, or we judge energy by the work that is done, because if there was no energy, there was not going to be work done. Why am I saying that? Because energy, the formula for energy, we get it by multiplying power by time. This is power by time, and that is work done. Work done across the period specified by that time. So then, what is power? We can define power from this equation again by, if we're looking for power, we can divide by time. Power is equal to energy over time. So what we are seeing here is that we have power being the work done over time. I hope you're all getting just the flow of these equations. So the simplest answer to this question is that no, power is the work done per unit of time. Work done per unit of time, or it is the rate. So when we are measuring, or when we always have time at the denominator, we're talking of the rate. This is the rate at which work is being done. The simplest way is the work done over time, which we define as work done per unit of time. So I hope you get that. So energy, power the rate at which work is done. That's it. So power is the rate at which work is done, or power is equal to the rate at which the energy is being dissipated. Simple as that. You can never go wrong if you try and kind of put this in a formula manner. Then from there you can put in your English to describe what is happening in that formula. Now we're going to look at question number 8.3. We are asked to calculate the resistance of X. They are telling us that the current, just going to erase these ones. So what I forgot to mention is that this switch is closed, and they are saying that the reading on this ammeter. I forgot to mention that a voltmeter measures the potential difference across that specific path or component that is being put across. Voltmeter across. Then the ammeter measures current, the flow of current, and we can't put it across, we're putting it in series. with this path. So current that flows here passes through the ammeter, we'll read what it is, and then it continues flowing. So they're telling us that that specific current now is 1.2 amps. So I want us to follow the current. Like water, current moves from the battery, conventional current moves from the battery, goes through here, and then it passes through the ammeter, it gets to this point. So what it sees is, oh, there's 6 ohms here. There's 6 ohms plus 2.4 ohms in that path. So they'll say, it's quite rocky here. This one is less resistance. So more current will be flowing here. And then less current will be flowing that side. But then they all meet up at this point because that's the end of that specific branch. They meet up here and reconvene to be 1.2 amps. And then it goes back to the battery. I hope you are getting how the current is flowing and the decisions that the current has to make as it's flowing through these different parts. So it comes back to the battery. So when they are asking us to calculate the resistance of X, we already know that X is dissipating that much power. And we know that power relates to current by I squared R. Please have a look at the equations at the bottom of this question paper. You'll see that there's a formula that says power is equal to I squared R. And what we know is the power there. Power is 5.76 and current is equal to 1.2 amps. This is squared multiplied by R. So to get R, we just divide the 1.2 squared. So R, so this one will cancel each other. 5.76 divided by 1.2. That's gonna be 4 ohms. 4 ohms. And we are going to move on to the next question, 8.4, which is asking us to calculate the total external resistance of the circuit. What is the total resistance external? So before we dive into this question, what do they mean by external resistance? Remember I told you that the battery has its own internal resistance and is being connected to a circuit that is outside of, let's say its body, or is outside of the confinement of the battery itself. So when you talk of the external circuit or external resistance, that's the resistance that is being seen by the battery outside of its physical nature. That means that we are referring to everything from here looking this side. Now I'm going to just erase some parts of the circuit that we don't need now. So when we talk of resistance, external resistance, this is a resistance that we see outside of the bit, and these resistors here, 1, 2, 3, 4. So how do we calculate this? Like I told you, current moves here, and it divides here. Most go this side and the other one goes this side, because here there's more resistance than this other side. And then it comes back, sums here to get back to that current. Now, why is it important to get the flow of current here? Where current divides, it means those different paths are parallel to each other. Where it convenes and becomes one, we're talking about a series connection. I'll repeat. Where current divides, that's parallel. Where it comes back and becomes one, that's a series connection. So it's series here, parallel, series. Now, what about these two here? If you follow the flow of current is going to move here, move here, move here. There won't be current going here. Now, why is that? This is not for the scope of this subject, but the voltmeter has too much high resistance. Now, if you can imagine, if the water is flowing and there's rocks everywhere here, the water cannot even get in. So it will always choose to flow this part where, of course, there's one or two rocks, but we can still move. So when you look at a voltmeter, it has a very high resistance, so current doesn't move that side. So we have current moving like this, and coming here. There wasn't current going this direction, so we're not having a convening. So current continues to flow there. Did it divide? No. So this is a series connection. So we already know that, 2.4 and 6 are in series. So 2.4 ohms and 6 ohm are in series. Okay, so we'll have to find out the total resistance of that. But also the current is branching here, which means that this 6 ohm is parallel to the summation of these ones, or this 6 ohm is parallel to the whole of that path. So 6 ohm, this specific 6 ohm is parallel to this. It's parallel to this guys here. And then this, the current here convenes, and this are a series connection. So when we calculate, we start with this series connection here so that we can calculate how parallel these ones are. So we say total of 2.4 plus 6 ohm is going to be R series is equal to R1 plus R2 plus R3. That's the formula for calculating series resistance. So we have only 2 there, which means we're going to say 2.4 ohms plus 6 ohm, which is going to give us 8.4 ohms. Now, this 8.4, we are going to say makes up these two resistors here. So what we are seeing now, the new circuit is like this. I'm going to just erase this. The new circuit now is like this. Now it is important to continuously draw these different stages of your circuit so that you can also follow in terms of diagram and never make any mistakes, or make it easy for the person who's marking you, that they see, no, this student or this learner actually understands what they are doing. So now we're going to say we have an 8.4 ohms here and we have a 6 ohms here. Then we have X, but we just calculated X to be 4 ohms. So, like I told you, these two are parallel. And what is the formula for parallel connection? 1 over R parallel is equal to 1 over R1, 1 over R2 plus continues like that. We only have 2 resistors there, so it's gonna be 1 over 6 plus 1 over 8.4, 1 over R parallel. So if you sum these two, you're going to get 2 over 7. So 1 over R is equal to 2 over 7. So we can do cross multiplication in there to find that Rp is now 7 over 2, 3.5 ohm. So we go back here and we have this circuit now as just one resistor with 3.5 ohms. You see that we have 3.5 ohms in series with 4 ohms. We're going to use the same equation here for series connection, where we say R1 will now be 4 and R2 be 3.5. So the final answer to 8.4, R external is equal to 4 ohms plus 3.5 ohm, which is going to be equal to 7.5 ohm. That's the answer, 8.4. Now we're going to have a look at question 8.5, the reading on voltmeter V2. Alright, so they are asking us what is the reading here when the switch is closed and we have 1.2 amps flowing. I want you to listen carefully for this explanation. There are many ways of finding the current in a specific parallel connection. One can maybe, so we've just calculated the total resistance. You can find out how much voltage is being dropped across this resistor, the internal resistor, and you then say that voltage should be available at this point. Then you start calculating going that side. But I have a simpler way, which once you get adapted to it, you'll always find electrical circuits easy and enjoyable. So let's go to easy. When current moves, I told you, look at it in terms of water. If water sees that this side is constricted, it's tough to move that side, but there's a flow or there's some opening this side, it was going to go there, then minimal water is going to go in the side of no more resistance or rocks or whatever. So what do we say in terms of current? Current moves here, more current goes this way. More current goes this way because there's less resistance here. There's more resistance here, which is 8.4, like we calculated. But how do we find the specific current that goes here or here? How do we know how it divides? Because we know here at this point, it combines again and becomes this 1.2 amps. Because if we know what is the current here, then we can just use Ohm's law to say I times R is going to give us the voltage on that voltmeter. So how do you calculate that specific current? So I need you to know that this is a ratio, it's just a ratio point of view. Current, let's call this I2 and I1. I2, this is the formula. I2 is equal to, so when we're doing a ratio, we're trying to multiply the current that is coming in here, so the actual I. We're trying to make it proportional or calculate the ratio that will move this side, and we should know that that is dependent on how much resistance that is on this side and how much resistance is on this side. So for I2 is going to be 6 ohms over 6 ohm plus 8.4. 6 plus 8.4. So every time we're trying to figure out the current here, we use this resistor at the numerator. Please understand that. We're trying to find the smallest ratio to multiply to our current here. When we're trying to find I1, what are we going to say? So we always at the denominator have the summation of the two, but at the numerator we use the opposite side as the numerator. Now for I1, what are we going to use? Like you guessed, it's gonna be the resistor on the side, the resistance 8.4 divided by 6 plus 8.4. Now I want to show you why all of this will sum up to 1.2 amps. If you calculate here, it's gonna be 6 over 14.4. That's going to be 14.4 times by 1.2 amps. The current is going to be 0.5 amps. Now here we also multiply by I, which is going to be, if we substitute 1.2 here, here the current is 0.67 amps. So to prove that this indeed is working, if we sum I2 plus I1, it should give us 1.2 amps. So we know that I2 is 0.5, that one is 0.667. Sum that, it's gonna be as 0.5, and that's 1.1666. So if we round off all of this thing, we are getting back to 1.2 if we're only looking at two digits. Now, I hope you got that. When we're trying to find different currents at different parts on a parallel connection, we just use the ratio. It always works. But please understand why you're using it. So, now we know that I2, the current that is flowing here, is equal to 0.5 amps. So how do we know, or how do we calculate the voltage on V2? V2 is equal to I2 multiplied by R. R is equal to 6 ohms. We times it by 0.5. So the voltage in there is 3 volts. That is our answer. Please go back to the steps that I've just alluded here and make sure that you understand them. Once you understand them, electrical circuits will always be easy for you. Let's go to the last question and then we're done. All right. Okay. So that's the question. The statement now says that a length of wire of negligible resistance. Like I said, when they say something is negligible, we don't need to consider it. It is not there. So it's 0 ohms. Is used to connect point P to Q. So they are saying they are replacing what is on the circuit by a wire and a wire here. Let's just try to redraw. It's going to be something like this. Oh no, sorry. So they are saying from point P to Q, we'll replace everything that's here by a wire. Make sure you draw this so that you understand what is going on. So that's going on B, our 6 ohm there. So we're going to have 6 ohms here and 6 ohms here. This is going to be 0 ohm, 0 ohm, because it's a wire of negligible resistance. This is just looking from this point going onwards. We're going to, of course, have our ammeter here. So they are asking us, how will the reading on V1 be affected? Okay, let's actually complete the circuit. It's gonna be something like this. Okay, sorry for my bad drawing, but we're trying to figure out how much will, they're asking, will this voltage V1 be affected by this change? Now please understand, okay, V1, so all of this, let's say, as they have stated, the switch is closed, which means there is current flowing here. There is current flowing here. And now they're asking us, the voltage that is being read here, will it be affected if we decrease the resistance of this circuit? I'm saying we decrease the resistance of this circuit. Why am I saying we decrease the resistance? Because here at this point we have changed that resistor to make it just a wire, which means that we're no longer dropping any voltage, we're decreasing the external resistance. So let's know that E or EMF is equal to, EMF of the battery is equal to the I external multiplied by R external plus R internal. Do we see that? So we're saying that the current that is moving through so in order for us to know the EMF of the battery, we should charge it by how much current is flowing here and the total resistance. So when we're reading, so when we just divide this, so it's IX multiplied by RX plus IX multiplied by R internal. So I told you that the voltmeter here, if it's not this open circuited, then there's no current flowing here. So there's nothing that is being dropped across this resistor. So we'll have that 12 volts that we already know. But if there's current flowing here, we're going to have C12 minus that resistance, and then it's going to tell us how much voltage is being read here. So do know that the internal resistance is constant. It's constant because, let's say, after 5 days or 20 years, the battery will have sort of depleted or had a certain resistance. It's no longer giving us the voltage that we bought it to be for. So we'll have a certain internal resistance. Now, what is varying here is the current that you're passing here. Know that as the current increases, it means there's more drop that we're going to experience here. So V1 is going to be equal to the EMF. So let me just try to explain to you in this circuit. So what do this all mean? So the EMF is made up by the voltage V1 plus the voltage of the internal resistance. V1 is the voltage that is actually seen by the circuit after we've went through this resistor. So we're trying to figure out if we keep this guy constant, but then now we are varying the I that is experienced by the circuit. Now ask yourself, when you decrease resistance, what happens to the current? When you decrease resistance, what happens to the current? Current goes up. So voltage is equal to I times R. And the current is equal to V over R. So when you decrease resistance, what you're going to have is that the current of the external circuit is going to increase. So if this is more, this one is going to go up. And when this goes up, it means the voltage we're dropping on our internal resistance is going to increase. And therefore, V1 will decrease, because V1 is equal to EMF minus the V of the R internal. So if this increases, then the voltage across V1 is going to decrease. And the reason is that the external resistance has decreased, which means more current, and therefore for more current, we're going to drop more voltage on our internal resistance. Therefore, the V1 is going to decrease. Thank you. Please leave questions below if you don't understand any of the questions. Thank you.